Hi everyone, I'm Cheryl. In this problem, we're asked to find the center of mass of the solid, which is a hemisphere of radius r. And we're going to be doing this using spherical coordinates. Okay, so when I take a look at my solid, the first thing I notice is that because of symmetry, I can tell that the center of mass will have an x-coordinate of 0 and a y-coordinate of 0 as well. The only piece missing is that z-coordinate. How high up do I need to go to get to my center of mass? Well, I know that I can calculate the center of mass, the z-coordinate, of the center of mass by taking the moment about the xy plane and dividing it by the mass. So let's go ahead and take a look at these components. We'll start out with the mass. Okay? So the mass I can evaluate using a triple integral. However, I also notice that because this is a geometry shape, a hemisphere, I can just use a geometry formula to calculate the mass. Now remember what mass is. It is going to be not just the volume, but the density times the volume. So we'll have density times volume. Now our problem did tell us that we had uniform density, so our density is just going to be a constant K. Our volume for a hemisphere is going to be 4/3 pi r cubed. Now that's the volume for a sphere, so since I only have a hemisphere, I want to multiply that by 1/2. So I can cancel here, and I'm going to end up with 2 pi all over 3 times r cubed, K, for my mass. Okay, the next piece to this puzzle is I need to find out what that moment is about the xy axis. So the moment about the xy axis can be calculated by using a triple integral, and I'll have the density function times the distance to the xy plane, which is z, dv. Okay, now I was asked to use spherical coordinates, so I'm going to convert this so I'm using that type of coordinate. The first thing I'm going to notice is that this density function is just a constant, so that can be pulled outside of my integral altogether. So I'll pull the k out. Okay. Z, I know in spherical coordinates, is going to be rho times the cosine of phi, and dv is rho squared sine phi d rho, d phi, d theta. All right, so now let's look at these limits of integration that I need. I'm starting to integrate with respect to rho. I know my sphere has radius r, so I'll be going from 0 to r. Okay. Phi, I'm going to be going from 0 to pi over 2. And theta will be going from 0 to 2 pi. Okay, so now I can go ahead and look at that first integration problem. Now, maybe before I do that, I'll notice that I have a rho and a rho squared, so I can combine that to be rho cubed. So I'll have a k times the integral from 0 to 2 pi, and the integral from 0 to pi over 2, integral from 0 to r. I'll write that as rho cubed cosine phi sine phi d rho d phi d theta. Okay, now again, that inside integral. I'm integrating with respect to rho, so that's going to be rho to the 4th over 4 And since phi is going to be treated as a constant, this will just be cosine phi sine phi. Evaluated from 0 to r, and I still have d phi d theta. Okay, plugging in my value r, I'll have k times the integral from 0 to 2 pi, the integral from 0 to pi over 2, r to the 4th over 4, cosine phi sine phi. When I plug a 0 in, this whole term will be 0. So I'm just left with my d phi d theta. Now I'm ready for the next. Now I'm ready for the next integral. Okay, so k times the integral from 0 to 2 pi. If I'm integrating with respect to phi, r is going to be a constant, so r to the 4th over 4 is a constant that I can pull out. The integral of cosine phi sine phi, using a little substitution, is going to end up being sine squared over 2. So sine squared phi all over 2, evaluated from 0 to pi over 2 d theta. Let's move this over here. So now, plugging in my upper and lower limits, I'm going to have k times the integral from 0 to 2 pi, r to the 4th over 4, times the sine of pi over 2 squared. Now the sine of pi over 2 is 1. 1 squared is 1, and I'm going to be dividing by 2, so that will be times 1/2. Then I need to subtract what happens when I plug a 0 in, but the sine of 0 is 0. So again, that knocks that entire term out. So I have still d theta here. And so I have k times the integral from 0 to 2 pi of r to the 4th all over 8 d theta. Okay, I'm ready for my last integration problem. So that 8 will pull out, and I have a k over 8. R to the 4th is also a constant, so that pulls out. And the integral d theta is just theta, evaluated from 0 to 2 pi. Plugging in my upper limit, I have k over 8, r to the 4th times 2 pi minus 0, which is going to be, if I cancel, I'm going to have k r to the 4th pi divided by 4. So that's my moment about the xy plane. But remember what we're looking for. We're looking for the z coordinate of my center of mass. So I know I can get that by taking that moment about the xy plane divided by the mass. Well, I've already calculated the moment. It's k r to the 4th pi all over 4. And I've previously calculated the mass, which is going to be 2 pi all over 3 r cubed times k, which, with a little invert and multiply, k r to the 4th pi over 4 times 3 all over 2 pi r cubed k, I notice that my k's cancel, the pi's cancel, r cubed goes into r to the 4th r times, and I end up with 3r all over 8. So the z-coordinate for my center of mass is 3/8 of whatever the radius of my sphere was. I hope that was helpful. Thanks.